an alarm and I woke up at 7:15 today, and it is pure panic mode because I'm usually like on the way to school at that point in time. Rah. All right, so welcome back, Calcsters. We are talking about Chapter 2.1, Rates of Change in the Derivative. Yesterday, we got this basic introduction of what the derivative is, and just as a quick reminder, the derivative at a point is simply the what of the graph? The slope, which means you could probably estimate some derivatives already. We're not going to do it necessarily right now, but we'll see it, and you probably, not probably, guarantee you can do more than you think you can. Okay. Today, we're going to jump into physics stuff for just a few minutes. So here we go. We're still in 2.1, but there's immediate application. So I called this velocity in my notes. I'm going to call this physics right now. Physics applications. Now, we will come in and out of dealing with physics applications in here. There are some really awesome applications of calculus and the techniques that we use that wind up everywhere in industry, from like if you're 3D printing, you're going to be doing physics stuff. If you've ever seen CAD software, computer-aided design and drafting, all of that is using calculus within the code to do all this. So to get started with this, we are going to first give ourselves a nice definition, and it's not super nice, but we need to make sure that we understand what it means. We're going to be discussing in here pretty regularly what is known as rectilinear motion. Now, this seems scary, and that word is pretty ugly, but we know at least what part of the word means. Linear motion just means straight lines. So paths that are easy, and maybe they won't always be, but for now we'll jump in. What about rect? Anybody recognize that word anywhere from math? Like a rectangle. And how many dimensions does a rectangle have? So that's sides. How about dimensions? If you want to draw a rectangle, you need a length and a width, or a width and a height, or however you want to call them, x and a y, right? So two variables, straight lines for now. Okay, now, when we go through this, this is really important. We're going to define it, and then we need to make sure we agree on the notation. When we're looking at this just simply moving in a straight line. That's all rectilinear motion is. Moving in, and I'm going to just say line, because every line that you've ever drawn is straight. If it's not a straight line, it's a curve and not a line. Okay, moving in a line. Now, and this is just a weird idea, when we start talking about timing stuff in physics, if I want to know how long something happens, like I'm about to drop this, and I can't pause time, unfortunately. Or I can, but maybe not for everybody else. If I'm going to drop this, the second I drop it, it falls, right? But if I want to know what's happening the instant that I let go, it's like we have to freeze time as soon as I let go. The instant when we begin, what time should we say we typically start at? 0. And that's like, I know that it's really 0.000000001, but the instant that we start, we're just always going to assume that that is where we're beginning. So our first little comment, when? What do you think lowercase t represents? Time. What if we're capital T? Temperature. Love it. When t equals 0, an object, whatever it is, doesn't matter. It could be a point. It could be the space station falling from the sky. I don't want to say who cares, because that'd be a huge deal. But the object, whatever it is at its, and I'm going to sneak in another vocab here, but we're not going to define it, initial condition. Now, later in the year, we'll look at a specific branch of calculus called differential equations, where this initial condition comes in all over the place. Okay, if you've ever seen chaos theory and double pendulums and how hard it gets to predict stuff, this is all based on initial conditions. And I actually hold a pretty strong philosophical view regarding the initial condition of our universe, but we'll get to that eventually. Okay, so right off the bat, I'm going to change color. This we all need to make sure that we have. And then we're going to use notation. Okay, there's one of two ways that show up. I know which one that I would prefer, but here's what we're going to have. If we have something that's written as S of t. Okay, S of t, this is your position. Position at time t. Okay, the alternative, and I'm not even going to write it here, but the other standard that people use is x. because when you're thinking about motion, you're looking at a change in some position, and the x-axis is a good place to start. Because x is such a common variable, we try to avoid it. I will try not to do any physics stuff with an x. It'll all be t. And we'll use s for what? S represents, how about s of t then? Because you're right. Position. This is our position. Okay. Now, I'm going to just see a little bit, whether you remember with physics or me or not. If we talk about how much my position changes over some amount of time, do you know what we have? Like, check it out. If I'm at 0, 0, and it takes 5 seconds, and I've walked to here, and it's roughly 5 meters away. 5 meters in 5 seconds. I was going 1 meter per second. That's my velocity, right? Now, the connection might not be there yet, but check this out. I literally just told you that the rate of change of this is velocity, right? What's another word for rate of change? Slope. Give me another new word that we learned yesterday for the idea of slope. What do you think the derivative of position might be? Oh my gosh, it is. So, not our main focus right now. I just wanted to front load that a little bit. V of t is our velocity at time t. One of the hardest parts of physics and what people struggle with over and over year after year is getting units straightened out. I'm not generalizing my units right here because they might change, right? If we're talking on the road out here, we're going to measure our velocity in miles per hour. If we're talking about a particle of light, you're going to measure it in meters per second. You could measure it in a bunch of things. Holloways per day. That'd be a weird way to do it, but that is a rate. Like, if my height is a measure of distance, then yeah, holloways per day is a measurement of something. Okay. What if we wonder how fast velocity changes? Like right now I'm walking at some speed, and all of a sudden I start slowing down. I'm accelerating. Now that was slowing down is a negative acceleration typically, but we have acceleration as well. Suggestions, and you're going to be right for acceleration at time t? A of t. Okay. We will see these over and over and over throughout the year in a variety of different contexts, and we'll even make that connection with the slopes or derivatives that we just addressed. Okay, so right off the bat, we're going to dive in and make that first one. If I wanted to find average velocity, just in general, how to find how fast is something normally moving, we will normally write, you could write average velocity, or we use v for velocity, and a bar above it typically indicates that we're talking the average. Okay, if I wanted to find my average velocity, and I think, did we do this yesterday at the start and end of the day question? Oh, do you want to hear something weird? Do you guys, I feel like we did this. Do you go to,
Going to bed in the same spot.
yeah, going to bed and waking up at the same spot? Okay, what do we say our average velocity is every day? And why is it 0? Because, you're right, but let's make that physicsy. My initial position, my starting position is my bed, and I end at my bed. What's the change in my position over time? Like, my displacement might be huge, right? Because unless you lay in bed all day long. But your displacement isn't what we're asking about, change in position. When we're looking at average velocity, what you guys were able to just tell me what it is. How do I write down concisely a change in position without writing the words change in position? Delta. If you take your change in position, delta, and I'm going to call it delta S for now. Sean, if there's a need to use S for seconds, I will. But if I just write S like this, we're not talking time, okay? Over time. Now, if we really wanted to find it, we could just take simply S of, and we're going to look at notation here. I'd only need 2 points in time, right, to find the average. If I use T1 here, and this is a weird idea, I'm going to make the claim that T1, T sub, remember a subscript, I'm just going to say T1. T1 is not my initial position. T1 is just the first measurement that we took. What was the time that we said we were at with the initial start of something ever? So if I take position at time 1, I need to subtract this position at time 0. So when we see this, we use this notation pretty commonly. Now, anybody remember how to say this other than T sub 0? and that's okay. Ooh, so take out the sub. This right here could be written and said as T sub 0. That's okay. More commonly and much nicer is T naught. Not NaUGHT is what we use for sub 0. Cool. Over, I'll switch back to my color. We just need time 1 minus T naught. Cool. Change the position over time. Nothing crazy happens, right? What if we wanted maybe a different way? Instead of looking at, I don't know, how fast is it going over some average course? Like if we imagined a ball dropping, and I'm going to have to do some stuff on this board, so it won't be on the video, but that's okay. Let's think about the flight of an object that's been thrown real quick. So everybody see this eraser? Okay, it just did a parabola, I think. It went, okay. If we wanted to measure its height or its position, something, we could graph it. And do you guys agree that if we wanted to graph the thing, we could say, hey, here's the time that it goes, and maybe we have its height. And it goes upward, 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 and then it comes down, and then it stops, right? Okay, if this is, height is like position, if we wanted to know what's the average rate of change from here to here, it's that same go to bed and wake up at the same spot, right? We started at height 0 and we ended at height 0. There's ultimately 0 change, right? Okay, my average velocity in that situation is 0. What if I wanted to know how fast the object was falling at, I don't know, this point in time? How would we even talk about how fast the object is falling? Now hold on here. I'm asking for a rate of change, right? And a rate of change is just a fancy way to ask for slope. Now, I'm not going to make us do this problem right this second, but if I take my lovely tangent ruler, don't rip down everything off my desk. Do you guys agree that when I first throw it, it starts going upward? Which means its velocity should be positive or negative? What's the slope that I check here? Like, you can't give me a number, but is my slope positive or negative? Okay, and then as it goes upward in the air, in the vertical direction, does it start slowing down because gravity pulls it? So if I look closer to where its maximum is, I still have a positive slope, it's still going upward, but is it slower? I can see the derivatives, my tangent lines, showing that the slope is changing. When it gets very up to the top, it stops before it comes back down, right? What would you say its speed is, or its velocity at that point in time when it stops? 0. What's the slope when we get to the very top? Oh my gosh, all these ideas are already here. Okay, as we're looking at it, what we're going to use is a little bit more formal version of that. If we want to find average velocity, that's all fine and dandy, that's an algebra question. What's way cooler than average velocity, however, is our instantaneous velocity. Now, I'm going to not, I don't know why I switched between caps and lowercase, strange. I'm not going to write the formal definition. What if we wanted the wordy definition of the instantaneous velocity? Anybody have a thought? And you'll see why I don't want to write it down. Talk to the neighbors, 20 seconds. I want to know, define for me instantaneous velocity. I'm calling on you, man. You're good, I didn't hear you. 4, 3, 2. Bea, I like what you said. Say it loud and proud.
Velocity at an instant.
Do you guys agree that that seems reasonable? What is the velocity at a single instant in time? Cool. The instantaneous. I'm not going to write all that. What I am going to do is I want to think about what that would look like. When we see V bar, it tells us this is V bar. It tells us we're talking about average velocity. When you see V without the bar, we are talking about instantaneous at this very specific point in time. So we're going to get real ugly for just a second. Okay. Well, if I want to know at a single instant in time, I need to make it so that my secant line becomes essentially a tangent, right? And the method that we used to do that yesterday was by introducing an idea that we talked about all of chapter 1. What allows me to move my secant line to a tangent line? Starts with an L and ends with limit. Okay, it's a limit. So let's take the limit, and notation is going to be ugly for just a second, okay? I'm going to write the limit as delta t goes to 0. Notationally, it's gross, but it's just because of the notation. What does delta t represent? A change in time. If we let that change in time be really small, that's the same thing as letting x plus h become really small, or it's letting x or c go to x, like the same thing. Okay, the limit as this goes, and you guys told me a minute ago that velocity is the change, and we wrote it even. Velocity is the change in what? Position. So here we go. We'll just use that exact same definition. So we'll say, okay, it's just s of t for any arbitrary time t. Notice we don't have a specific one here, minus whatever the position was at my initial spot that we're trying to check. And we're going to rock this out, t minus t naught. Turns out there's an easier way to write this. And we're going to do a problem with this. We're just finding the limit of the position is what's happening here. This whole expression says I'm taking the derivative of, what's my function? Instead of f of x, what do we write? S of t. So what I really want to connect here, and this part, sure, if it does, awesome. If it doesn't, less awesome, but we'll, okay. This is exactly s prime of t. Okay. We don't have a simple symbol for differentiate, which is what the actual word to take a derivative. So we're just going to leave it here for now. Let's do a problem together. Cool. Okay. Here's the deal. We're going to do one problem, and then we'll do our feelings, emotion day question. I don't know, whatever that question is. I don't have the alliteration in my head. Here we go. Example. Possibly, because I'm definitely giving you guys homework. Okay, an object moves. There's our first step. An object moves. Okay, don't care what it is. It's an object. I'm probably going to think about it as a massless object that's just a point. Cool. But it's moving. Its distance is given by a lovely equation, and we'll say that this is, and I'm going to write it ugly and we're going to talk about what it means, s, which they tell me is just a function in terms of time, and I don't like doing this, but I want to make sure that you see it, and we'll say it's equal to 2t cubed plus 4. All right, before we dive into doing the calc, it drives me crazy that this is the norm because you're never introduced it until you see it in a calc class. I haven't erased it. I also have towels all over that I use to erase because I hate these erasers. But as we're looking at this, when we see graphs and stuff, and you'll see it when we get to practice AP stuff, when I start printing those out, but pretty regularly, if I were to graph something, and this is just, we're just going to make the agreement that if I write on this board, it's just for us to talk about, okay? That way I don't have to worry about making cool combinations of stuff for colors. If I graph this function, is it possible that this is a graph of f of x? Here's what you're going to see over and over in AP Calc, except they're more formal. They say this is the graph of y equals f of x. And it seems redundant, and I agree with it, but that's exactly what they've done here. We have position, s, and it's determined by a function in terms of t. I don't like this notation. It doesn't always use it, and the AP College Board won't always use it. Anybody have a suggestion for what might feel more natural to write instead of this? If s is our position and is given by a function f of t. Does it seem more natural that we could just use this? Instead of saying position is given by a function f, could we just say there's a position function? These are the same thing, just so you know. I just want you to be aware that this will show up and you will see this. Okay, I hate it. I wish they didn't do it, but I didn't write your book. It's the only thing that I don't like about this book, legitimately. Anyway, I want us to find 3 things, and we're going to do one together as a class, and then I'll have you guys do B and C. I want us to find the instantaneous velocity when time is 0. Instantaneous velocity when, and did you guys already write 0? I'm going to say when time is 3, so it's a more interesting problem. Now, we're just going to work here. Let's assume we're finding instantaneous velocity. Let's assume that this is in meters here and time is in seconds. I won't even write it. That's a standard unless we're told otherwise, okay? Meters and seconds. So here we go. I need to find the velocity when time is 3, and I'm stuck. Conceptually, could we graph the position function? Like, not literally could you graph this cubic function right this second, but is there a graph of that function? 2t cubed plus 4. There is, right? It looks roughly, I'm not going to sketch it, and it's not important, but it looks roughly like this. It's just this, but moved up 4, so I guess it's like this. Okay, I'm fine with that. Man, we're given position and we need velocity. How on earth could we possibly do that? How do we find the slope of a tangent line to that graph? Okay, I'm going to call on one random person in 20 seconds. Talk with your neighbors. How do you find the slope of a graph at a single point? I think it just clicked in your head, I think. What are you going to say? Good. Or good. All right. So, hit it. Somebody said it. I heard Rafa say it. Anybody other than Rafa have a good way to word this? To find the slope of a function at a point. What did we talk about yesterday? What's this whole chapter? The next 3 chapters? We're looking for the derivative. That's it. Now, we're looking for a very specific derivative, so we're going to write this out. I did not have this written in my notes. Instead, the way that I would write this, instantaneous velocity at 3, it's literally just v of 3. That's it. Okay. Now, if we're trying to find it, and we are going to find it right now, let's try to knock this out. This is, up to you if you write this part, but this is the same thing as the derivative of s at 3. These are the same value. Interchangeable. Okay, now the question becomes, how do we do this? How did we define f prime of c yesterday? I'm going to write it up here just so we have it. Yesterday we said f prime of c is equal to the limit as x approaches c of f of x minus f of c over x minus c. Let's change this. In this one, s prime of 3 is exactly equal to the limit as, is our variable x anymore? What is it, Riley? So that's kind of. Let me be more specific. What are we plugging into the function? T. So I agree with you, s, and that's I asked that question poorly. But we're looking at the limit as t goes to what value? 3. Of, well, let's do, I'm going to write it out all the way first. We'll do s of 3. Nope, s of t, I'm sorry. Minus s of 3 all over t minus 3. Are we cool with that first step? All right, now let's just get cooking here. This is the limit as t approaches 3. What's s of t? 2t cubed plus 4 minus, I'm going to do some scratch work in my head, or you guys are. What's 3 cubed? Times 2? 54. Plus 4? 58. Do I care if you can mental math this or if you have to type it in? I don't care even a little bit. Do we agree it's 58? Cool. So I have 2t cubed plus 4 minus 58 all over t minus 3. All right. Questions? All right, thank you for clearing up, K-Rad. Cool. Now I'm really going to get stuck because we're going to do this without our calculator. I think that this is 2t cubed minus 54? That sounds right. Over t minus 3. Okay. Sans calculators. Without your calculator. If I try to x sub, it fails. I divide by 0. It's broken. What the F? Not. Oh, yeah. Abigail said it. Factor. Huh. And if you didn't hear JJ whisper confidently, difference of cubes. I'm going to factor something out first. 2. And then I'm not going to factor the difference of cubes. You guys are. Without your calculator. If you need your cheat sheet, use it. I'm going to give you a moment. Okay. There's our factorization. T minus 3 and t squared plus 3t plus 9. Something convenient happens, right, Kalisha? When I write this factorization, something real convenient just happened. The t minus 3s, they did what? Good call. I was going to yell. All right. Well, I thought I was expecting cancel. I don't know why I was expecting it. I wasn't really going to yell. Cool. What should we try now? 3 squared is 9, plus 9 is 18, plus 9 is 27. Okay, here is, oh, am I wrong? Times 2 is 54, just like I thought. Whoops. Cool. Here's the big part. This is so tedious and it's annoying. If you stop here, you won't get marks. You won't get credit for it. What did we really just say? When t equals 3, the velocity, and we didn't specify what it is, so we're going to have to just say what we said it was, which was a really weird thing to say just now. What do we say we're talking about? What is moving? Good. When t equals 3, the velocity of the object, and we have to be specific, is 54. And what were the units that we agreed on? Meters per second. And we have it. Cool. All right. I want you guys to do one more like this. We'll take a quick brain break after that, and then we'll knock out the bigger part of this. All right. On B, I want you guys to find me the instantaneous velocity when time is 0. I'm going to give you a head start. I need to see your limits that you're evaluating. We just found v of 3. I want you to find v of 0.